Okay then. So we've got so our first lesson then. If you would sort of follow me, and then you can. I'll show you around. Just remind you of what we did in our previous lessons. So our first lessons, we looked at all the different energy types that exist, and I guess uh, did we really define energy? We haven't really defined what energy is, but essentially, energy is if something has energy, it can do something. Um, it can make something happen. So whenever we see something happening, maybe something's emitting heat or light or making sound or moving, maybe, then that's a suggestion that it's got energy. And there are different types of energy, and I think we might not have said this point yet, but I'll say it now. Is that energy cannot be created or destroyed. There's a this this idea is linked to the conservation of energy. So, so energy, and so let's just make a note of what that is. So the conservation of energy is it states that energy cannot be created or destroyed. Um, and often what we say after that is that it can only be transferred from one form to another. Now, so when we looked at these different diagrams of these energy transfer diagrams, we can see that we had electrical energy was transferred or changed into light and thermal energy. And this is an example of what a light bulb does. When you plug in a light bulb, there is electrical energy and it's transferring into light energy and thermal energy. And then we have a fire. Sorry? So why can't it be created? Well, I mean, it's just basically part of the definition of what energy is. So one of the things that I read about this a little while ago, which I found even more interesting, is that if energy can only, in fact, let's put them, leave a gap. So we got energy cannot be created or destroyed. It can only be transferred from one form to another. Now, what this would mean is that there has always been the same amount of energy in the universe. In fact, you can say there always been the same amount. There have always been, and always will be, same amount of energy in the universe. Now, I'll mention here briefly that there is something that you'll learn about in A-level physics. You're doing A-level physics, right? Is that correct? So one of the things you'll learn about in A-level physics, and you won't touch on this much actually, is something called special relativity. Now, and this is linked to the equation. We won't really do it much now, and you don't even really do it much at A-level, but just in case you hear anybody saying that what I said is incorrect, then I'm only telling the whole story. Because actually it turns out that matter, or basically anything that is anything, like anything you can pick up or whatever, matter can be converted into energy. So strictly speaking, when I say there has always been, and there always will be the same amount of energy in the universe, technically what I should be saying is there has always been and always will be the same amount of mass energy in the universe, because mass can actually be converted into energy, and energy can be converted into mass. However, we're not going to really worry about that, because that only occasionally gets mentioned at A level, and it certainly doesn't get mentioned at GCSE. So we're going to kind of, I mention it now, just in case you read anything that says that, hang on a second, energy can be, there isn't always the same amount of energy, but there will always be the same amount of mass energy. Anyway, in general, though, there is energy cannot be created or destroyed. It can only be transferred from one thing to another. And there always has been and there always will be the same amount of energy in the universe. Now you say, why can it not be created? Well, the same reason why, I guess, it's just one of the fundamental laws of nature. It's just, I don't know how to say it. It just can't be. Based on the type of physics that we're looking at the moment. Okay. Now, as we learn more and more about the universe and more about how things work, we might realize that this isn't 100% correct. But certainly at GCSE, this is something that we take to be true. We learned that within all these different types of energies, you can have, some of them can be stored. And these energies are called potential energies. So, for example, if something is held up on a high place, like a book on a shelf, the energy is stored as gravitational energy. So the full name would be gravitational potential energy. The same is if you squash a spring, compress a spring, or if you stretch a spring. In that case, also, the elastic energy is stored, and we can say it's called elastic potential energy. And with chemical energy and nuclear energy. Now, kinetic energy is a bit confusing because we don't think of energy in a moving object as being stored, but it is. It's just in regular life, if we have something, let's imagine we had a ball rolling along the ground, and yeah, let's just draw a little arrow. So this ball is rolling along the ground. Maybe it's moving at 3 meters per second. Now, it's not going to keep moving at 3 meters per second, is it? It's going to eventually slow down. Eventually, it will stop. Now, and so it suggests that, well, there's no energy stored in it. But that's because the energy is being transferred. So I'm going to just pause the video now and see if you could draw for me an energy transfer diagram that happens when a ball is rolling and then comes to a stop. Okay, so you want to put an energy here, that's the input energy, and whatever energy outputs over here. And you can put those as the output energies. Okay, so I'll just pause that now. So we've got kinetic energy being converted into thermal energy and sound energy. Now, in this case, what we did before, we color coded the input energy as blue. So we could color code that as blue. I'm not so concerned about that at the moment. I just wanted to bring it up though because we did use the green for useful energy and the pink for wasted energy. In this case, however, this is just a ball just rolling along. We're not trying to actually cause something to happen. We're not trying to make thermal energy. We're not trying to make sound energy. So I suppose if you want, we could color them both in pink. But we're not so interested in what we're... this is not a machine that's been designed to do anything. It's simply a ball rolling along the ground. But it does link to something else, and that is, where is the energy now? If we had some kinetic energy rolling, being converted into thermal and sound energy, where is the energy now? Where's it gone? So I'm going to just pause the video and let you have a think about that. And if you want, you can write your thoughts down. But let me just recap that question again, just so you understand what I mean. We had some kinetic energy. It was converted into thermal energy and sound energy. Now, in no time at all, we can't hear any sound, and the ball is not warm, the ground is not warm, so where is the energy now? So this is often a confusing topic. If I try to detect any energy after this ball has rolled along the ground, I won't be able to find it. It seems to have disappeared. But the conservation of energy says that energy cannot be created or destroyed. If you just want to follow me again. So let's just try to understand how this might, or why this might be, or how could this be explained. I'm just going to just shrink that a little bit. It's to do with energy dissipation. And really what dissipation means, it basically means spreading, it means spreading out. So the energy has been spread out. It's spread out so far that it no longer makes a difference. Let's imagine we had a load of thermometers. I don't know how good I'm going to be at drawing a thermometer, but I'll give it a go. Oh dear, that's terrible. I'm going to pause the video and get a picture of a thermometer. Okay, so let's imagine these thermometers measuring different places along the ground. One of them is measuring the place where the ball was rolling. One of them is measuring the ball. One of them is measuring the air, and so on. Well, you might find, if the thermometer is sensitive enough, that there is a slight increase in temperature on the ball, a slight increase in temperature where the ball rolled. But gradually that heat spreads out, and then so the energy distribution, the way that the energy is shared around spreads out, and so it becomes more and more normal. And remember, it's not just going to be the actual floor, it's not just going to be the air, it's going to be the entire universe. So the Earth is giving out heat into space, and that heat travels and travels and travels. Eventually, it gets so spread out, it can no longer be detected. So that's really the main point. The energy is so spread out, it can no longer be detected. This is the idea of energy dissipation. It's not being destroyed. We just can't see it anymore because it's all spread out. Okay, so we've got different types of energy. We've got some of them can be potential, some of them can be stored. We call those potential energy. The conservation of energy is that energy cannot be created or destroyed. There's always been the same amount of energy in the universe, and that when it seems as if the energy's disappeared, it's not disappeared. It's simply been spread out. It's been dissipated. After that, we looked at some Sankey diagrams, which just showed. If you want to make sure you keep following me, it just showed how the energy could be transferred. Usually, energy is transferred into more than one type. Maybe always it's transferred into more than one type. So we have a light bulb. If I gave it 100 joules of energy, I might only get 20 joules of light and therefore 80 joules of heat. And this can be shown using something called a Sankey diagram. This is called a Sankey diagram. And we use the width of the arrow. The width of the arrow represents the amount of energy. So 10 centimeters here represents 100 joules. That would mean that 1 centimeter must be equal to 10 joules. And so 2 centimeters is 20 joules, 8 centimeters is 80 joules. I can work out how efficient it is by saying how good is it at making the useful energy. And if I only got 20 joules out of 100, then it's 20% efficient. And you can work out efficiency using this. Oh, and then times it by 100%. Then we looked at some other energy equations, and these were we got energy efficiency one down here. Then we got the different types of energy, how to calculate kinetic energy, how to calculate gravitational energy, elastic energy. Oh, some of these seem to have disappeared. Oh, I don't know what happened there. I'll rewrite those in a moment. So we got these different types of energy and thermal energy and electrical energy. Yeah, I'm not quite sure. Some of these things seem to have disappeared, but we'll correct it shortly. And then we've got power. Power is not energy at all. Power is how quickly the energy is transferred. So if something can transfer energy very quickly, very easily, very quickly, then it's powerful. That's what powerful means. So this one would be able to transfer. We know a car uses transferred chemical energy into kinetic energy. Well, it also produces heat and sound. So it's not about how efficient it is. It's not about how little is wasted. Power is about how quickly it does this. So it could still be quite inefficient. It could still actually waste a lot of energy, but still be quite powerful. So it's about how quickly it does that. This one on the left may take a longer time to transfer the chemical energy into kinetic. The one on the right might be able to do that much more quickly, and so it's more powerful. Okay, so we're going to probably do a little bit more work on these equations today. But I think we'll leave it. Let me just grab that there. We'll leave it there, and I'll stop the video, and I'll just maybe save it. Maybe I'll save it here, and I'll also put it in your Notion page.